Welcome to the deep dive. Today, we're diving headfirst into, well, one of the biggest puzzles in physics, really. It's this century-old standoff between general relativity and quantum mechanics.
It's a fundamental clash, isn't it?
Totally. I mean, for decades, these two theories, they've been pillars, incredibly accurate in their own zones, but try to bring them together and, well, they just don't mesh.
Mm-hmm. Completely incompatible, it seems.
Exactly. You've got general relativity painting this picture of a grand cosmic ballet, smooth space-time, warping under mass and energy. That's your gravity, planets moving, the big picture.
Elegant. Continuous.
Right. But then quantum mechanics, it throws you into this completely different world. Probabilistic, jumpy particles doing, frankly, weird things, collapsing wave functions, non-locality.
Yeah, the quantum realm is famously counterintuitive.
So our mission today is to explore this pretty surprising new framework. It's called motion theory, and it claims, quite boldly, that it can bridge this gap with just one core idea.
And let's say, the aha moment we're aiming to unpack is that maybe it's not a contradiction at all. Maybe it's never been a contradiction. Yeah, perhaps it's more about perspective. Or, as we'll get into, a difference in, let's call it resolution.
Okay, resolution. Intriguing. Let's tackle this unbreakable divide then. What we thought was unbreakable, maybe just a quick refresher, general relativity.
Sure. So GR, Einstein's theory, it basically says space-time isn't just a static background. It's like a fabric, right?
Classic trampoline analogy.
Yeah, exactly. You put something heavy on it, like a star or a planet, it creates a dip, a curve. And other things rolling nearby follow that curve. That's gravity.
And it works beautifully for, well, everything big. Planets, galaxies, black holes.
Phenomenally well. But then you zoom in, way, way down.
And you hit the quantum world.
Right. And suddenly, reality isn't smooth anymore. It's discrete. It's about probabilities, particles being in multiple states until you look.
The infamous measurement problem, that quantum weirdness, it feels fundamentally different.
And that's the crux of the conflict, historically. GR needs smooth, continuous geometry. QM runs on these discrete, probabilistic jumps. They describe symptoms brilliantly at their own scales.
But no connection, no underlying reason why they're so different.
Exactly. They lack that unifying root cause. Until, perhaps, now.
Which brings us back to motion theory's claim. It's a difference in resolution. What does that actually mean in practice?
Okay, so the idea is this. General relativity isn't describing something fundamentally different from quantum mechanics. It's just describing motion at a different scale.
Like looking at a picture from far away versus up close.
Kinda, yeah. GR describes the macro-scale, low-frequency structured motion. Think big, slow, coherent patterns. Planets orbiting, galaxies drifting. Predictable.
Okay.
Whereas quantum mechanics describes microscale, high-frequency structured motion, think incredibly fast, intricate, maybe less stable patterns, the underlying buzz of reality.
So the weirdness is just high-frequency complexity.
In a way. And crucially, the theory says there's no sharp dividing line. It's not like you cross a border and suddenly physics changes. It's a continuous scale shift in motion resolution.
Wow. Okay. That's a big shift in thinking. So let's really dig into that. General relativity, things like mass, gravity. How does motion theory even begin to reinterpret those? They seem so fundamental.
They are fundamental concepts, but motion theory suggests their nature is different from what we assumed. It reinterprets them through this lens of structured motion. Let's take mass.
Okay, mass. What is it if not just stuff?
Well, in this view, mass isn't really a thing itself. It's described as the local resistance to motion resolution.
Whoa. Okay. Resistance to motion resolution. Can you break that down a bit? Like an analogy, maybe?
Sure. Imagine like a whirlpool or a very tight eddy forming in a smoothly flowing river.
Yeah.
That eddy isn't a solid object, right? It's just water moving in a complex, structured way.
Right. Pattern of motion.
Exactly. And that highly structured pattern resists being easily smoothed out or resists other patterns flowing through it. It takes energy to disrupt it or change its flow. That inherent resistance of a structured motion pattern to resolving into a simpler state or interacting smoothly, that's what we perceive as mass.
So more complex, tightly wound motion structure equals more mass.
That's the idea. It's about the density and stability of the motion pattern itself.
Okay, that is a leap. And gravity then? If it's not space-time bending, what is it?
Gravity is re-envisioned as convergent synchronization.
Convergent synchronization.
Yeah, think of it like motion structures are naturally drawn towards regions where other motion structures are more densely packed and synchronized, like tuning forks vibrating together,
Hmm.
or dancers moving towards the most rhythmic part of the floor.
So things fall towards massive objects because the motion patterns are denser and more synchronized there.
Essentially, yes. Motion naturally flows towards zones of higher sync density. It's not a pull, it's a convergence of rhythmic patterns.
And space-time curvature, that iconic image.
That's seen as motion trajectory adaptation. It's not the space bending, it's the paths of motion adapting as they navigate regions where these underlying motion loops are highly compressed or structured.
So the paths change, not the stage itself.
Precisely. And things like time dilation, length contraction, those relativistic effects, they become loop deformation responses. The motion loops themselves stretch or slow down their rhythm based on synchronization constraints when systems move relative to each other.
So it all comes back to the motion, the synchronization, the loops.
Exactly. It's not about warping space. It's
Yeah.
about the convergence of synchronized motion toward high-density rhythmic zones.
Okay, mine's slightly blown on the GR front. But now, the quantum side. This is where things always get, well, weird. If GR is about synchronized motion, quantum mechanics feels like the opposite uncertain, probabilistic. How does motion theory handle that? Does it say quantum mechanics isn't actually random?
That's arguably the most radical part. Yes, it suggests quantum systems are not fundamentally probabilistic or random.
Really? But what about, Schrodinger's cat, the uncertainty principle?
Motion theory proposes that quantum systems are actually pre-structured motion loops that haven't fully resolved.
Pre-structured. So the potential is there, but it's not settled, like a blurry photo.
Exactly like that. Think of a complex vibration or a chord that hasn't quite hit its final stable note. It has structure, potential, but it's still in flux.
And measurement, what we thought was collapsing the wave function.
That's reinterpreted as forcing synchronization with the observing system. When you measure your instrument, your interaction, it provides an external constraint. It forces that unresolved motion configuration, what we call the wave function, to stabilize, to resolve into one definite pattern.
To collapse isn't mysterious, it's just interaction causing resolution.
Correct. Collapse is simply an external constraint triggering loop resolution. The environment forces the pattern to pick a state, essentially.
Okay, and entanglement, that spooky action at a distance.
It's also demystified, supposedly. Entanglement is seen as two loops entering shared synchronized phase. Their motion patterns become linked from the start.
So they're not sending signals faster than light, they're just already dancing to the same beat, even when separated.
That's the picture. Their underlying rhythms are locked together. And uncertainty, Heisenberg's principle.
Yeah.
That's understood as the natural ambiguity before full sync stabilization. Of course, you can't pin down all aspects of an unresolved fluctuating pattern perfectly. There's inherent fuzziness until it resolves.
Wow. So the quantum weirdness, the probabilities, the collapse, it's all because we were looking at unresolved motion patterns and mistaking them for fundamentally random things.
Precisely. The theory argues the strangeness comes from assuming particles and forces are the fundamental reality, rather than seeing them as artifacts of loop phase behavior. It's all motion, just behaving differently depending on how resolved or synchronized it is.
Okay, let's pull back a bit. We've got GR as large-scale, synchronized motion, QM as small-scale, unresolved motion. How does this motion resolution idea actually unify them? What does the big picture look like now?
The unification comes from realizing they aren't describing different kinds of reality, but the same underlying process-structured motion viewed at different levels of detail, different resolutions.
So it's like zooming in and out on that same river. Far away, you see the main flow, the large eddies.
Right, that's your general relativity. At those large scales, the loops are coherent. They're stable, synchronized structures that behave predictably. Planets, fields, chairs, you name it.
And then you zoom way in.
And you start to see the tiny turbulences, the complex, high-frequency fluctuations within the water itself. At these small scales, loop resolution is incomplete. The patterns are still forming, interfering, drifting in and out of phase.
And that's where you get the quantum effects, the
Yeah.
wave-like behavior, the interference.
Exactly. That's the quantum realm. So the key insight is there's no fundamental division. It's not two separate sets of laws. It's just a continuous spectrum of motion complexity, all arising from the same basic principle of structured motion resolving itself.
That is elegant, actually. A continuous spectrum. What about the fundamental constants? Things like c, the speed of light, or Planck's constant h bar, where do they fit in a universe made of motion?
They fit in beautifully, actually. They're not just arbitrary numbers plugged into equations. They emerge from motion limits within this framework.
Okay, how so? The speed of light.
The speed of light, c, is proposed to be the maximum sync propagation speed. It's the ultimate speed limit for how fast a change in a motion pattern or synchronization can travel through this motion framework.
The cosmic speed limit for information, but framed as motion sync speed. Makes sense. And Planck's constant, that tiny quantum number.
Planck's constant is interpreted as the minimum resolution unit of structured loop rhythm. It's like the smallest possible beat or quantum of action within these motion loops.
So it pops up where the macro meets the micro, because that's the scale where the individual beats of these loops become noticeable.
Precisely. It signifies the threshold where the granularity, the discreteness of the motion resolution becomes apparent. So both GR's smooth-seeming fields and QM's discrete packets are just emergent features of rhythmic motion resolution limits.
Okay, this is painting a very coherent picture, which leads to the question, if motion is the root cause, why did GR and QM fail to unify before? Why did they break when pushed into each other's territory?
Well, the argument is because they describe symptoms, not the root cause. They were incredibly successful descriptions of phenomena at their respective scales, but they didn't capture the underlying dynamic.
Like describing how waves look without understanding water.
Something like that, yeah. GR assumed continuity but couldn't grasp the discrete quantum world. QM assumed probability but couldn't generate the smooth coherence of gravity. Motion theory claims to provide that missing foundation, structured synchronization across constraint gradients. That's the engine driving both sets of symptoms.
This really reframes the whole endeavor. It suggests the contradictions we saw weren't real. They were artifacts of incomplete descriptions. Motion theory doesn't just connect them. It seems to dissolve their contradictions.
That's the claim. Suddenly, you don't need to find a way to quantize gravity, force it into discrete packets. Why? Because gravity, in this view, is already just a large-scale manifestation of converging, synchronized motion patterns.
It's emergent from the motion itself.
Exactly. And you don't need to find elaborate explanations for entanglement spookiness. It's just loop sync across scale, a natural consequence of how these motion patterns link up.
It feels less like adding a new theory and more like revealing a deeper layer beneath the existing one.
That's a good way to put it. The ultimate takeaway is quite profound, really. Reality isn't fundamentally made of things, particles, fields, space-time fabric.
It's made of motion.
It's made of motion. And everything else, every equation we write, every theory we build, every paradox we encounter is just our attempt, our evolving description of that one fundamental substrate, structured motion resolving through rhythm across all scales.
Structured motion resolving through rhythm across all scales, a truly fascinating and potentially game-changing perspective to think about. Thank you for joining us on this deep dive into what might be the future of physics. Definitely gives you something to ponder. Keep exploring, keep questioning. We'll see you next time.